Okay, let's get into the basics of chemical formulas and nomenclature, so the naming of compounds. The basics to start with, when you write a formula, the subscript indicates how many of that element are present in the molecule of the compound. So with hydrogen, you've got H2, so there's two hydrogens in the compound. For carbon dioxide, you have two oxygens and one carbon, so it's CO2. Pretty basic. Molecular compounds are composed of molecules and almost always contain only nonmetals. So when we talk about molecules, molecules are when we're referring to just nonmetals combining together to form substances. Okay, out of all of the elements on the periodic table, these 7 are always written as they're diatomic molecules. So you've got hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And these you just have to memorize. So like if you ever come across a problem where it says bromine gas combines with such and such metal to form this, when you're writing the formula out, you need to make sure to write it as Br2. Don't write it just as Br. So just having this grouping of nonmetals memorized as diatomic molecules when you're writing the element down, it's really important to keep that in mind. All right, so we're going to talk about types of formulas, and with that we've got, so there's the idea of empirical formulas, which gives the lowest whole number ratio of atoms in each element in a compound. So if we've got, and sometimes the molecular formula is not the same as the empirical formula. So the empirical formula of a compound, and these are for molecular compounds, is the whole number ratio, and the molecular formula is the actual number of atoms in each compound. So like if you think of sugar, or let's think of glucose, which is C6H12O6. Okay, so that is the molecular formula. If we were to write the empirical formula for glucose, we would write it as CH2O, because if we were to simplify all of the subscripts for glucose, which is C6H12O6, it would simplify by dividing all of them, by dividing all the subscripts by 6 and simplifying them to a 1 to 2 to 1 ratio. All right, when we talk about types of formulas, there's different ways that we represent them. So you've got structural formula, you've got perspective drawing, so where you draw some of the bonds within the plane of the paper and some like going back behind and some coming out front, trying to represent the three-dimensional structure of a formula. And then you've got the ball and stick model as well as the space filling model. And perspective drawing is mostly common when you're talking about organic compounds. So definitely, like if you go on to take organic chemistry in second year college, usually that's the typical time that you would take it. Then developing your ability to do perspective drawing is there. All right, sorry about that. Okay, moving forward. Okay, we're going back here. Okay, so anyway, perspective drawing comes more into play when we do organic chemistry. All right, another type of compound when we are looking at it would be ionic compounds, and this is when ions are present. And we actually spent a decent amount of time looking at ionic compounds in first year chemistry. But the ions are when an atom either loses or gains electrons to become ions. Cations are positive and are found more so on the left side of the periodic table, and anions are on the right side, mostly nonmetals that form anions. And they're negative and positive, and most of the transition metals, which we'll look at a little bit later, also have positive charges or form cations. And they lose electrons or gain electrons to have a more stable outer shell of electrons. And we'll look at that further on in this course. when we make ionic bonds or ionic compounds. Ionic bonds are when negative and positive ions come together to form a lattice, or basically a charged lattice where you've got positive and negative ions. And if you think of it, this the exchange of electrons. So if you've got the example here being sodium chloride, sodium has one extra electron, and chlorine would love to gain one more electron to have 18, and sodium likes to lose one to have 10, to have that full outer shell. And so therefore they react very readily, chlorine gas with sodium metal, to form sodium chloride. Okay, when we write ionic formulas, one of the simplest ways, at least with ionic compounds, is just take the charge, and whatever the charge is associated with the compound, that becomes the number of the other thing that you need to balance out the charge. So example here, magnesium has a 2+ charge, nitrogen has a 3- charge. So for magnesium nitride, you would need 3 magnesium, so Mg3, and 2 nitrogens to balance out the charge. So the overall charge of the compound is 0 by having the same amount of each as far as by charge. And keep in mind that if the compounds are not in the smallest whole number ratio, you want to simplify ionic compounds down to the smallest whole number ratio. So let's say for whatever reason you had Mg6N4, you would want to simplify that down to Mg3N2. So whole number ratios for ionic compounds. And that's because technically ionic compounds, they aren't molecules, so it's more so, think of it as a lattice of just repeating patterns of like 3 magnesiums, 2 nitrogens over and over and over, where a true molecule, like when you think of water, water is made up of 1 oxygen, 2 hydrogens, and they are independent of each of other water molecules, where like magnesium nitride as a ionic compound is just, it's constantly repeating, and that's why most ionic compounds are solids. They aren't, they don't behave like molecules. All right, and you had review as far as over the summer to look at the common cations and to become familiar with most of their charges. And as we continue in this course, a lot of these you're just going to memorize, and some of them you already have memorized, but as you use them more and more, they'll just become commonplace as far as your ability to be like, oh, ammonia, NH4+, and you know the charge and you know how to work with it. Same thing goes for common ions that you'll interact with. One that when you were probably starting out in chemistry threw you off as far as acetate, or the acetate ion, which also is part of acetic acid. That one, originally, it can also be written different ways. So in this form, on this table, it's CH3COO minus, but you can also sometimes see it as C2H3O2 minus, as it's written there. So just be familiar with that. They become more, you get used to them as you interact with them more and more. All right, so when you name an inorganic compound, you want to write the name of the cation, and it's just the name, right? So let's say we're talking about barium, so Ba2+, you're just going to write the name, it has no change of it. And then for the anion, and it's just the element form, you use the IDE ending. So let's say it's with bromine, so it would be BaBr2, but to say that would be barium bromide. And the "ide" indicates that it's the elemental form of that compound as an ion. And if the cation can have more than one possible charge, then you need to write the Roman numeral. So that applies when we're working with transition metals. So example being iron. Iron can either be +2 or +3. So if it was a +2 iron ion, we would want to make sure to write in Roman numerals the number Roman numeral 2 in parentheses after we wrote iron, so that it was clearly that ion that's present, especially in the name. All right, and then when we get to oxyanions, so Examples being nitrogen combined with oxygen, sulfur, and you can also have phosphorus combined with oxygen, a few others. But there are some patterns in how we name it. So there are kind of standard. So nitrate, you can have sulfate. So nitrate is NO3 minus. Sulfate is SO4 2 minus. So if you have one fewer oxygens than what is the standard, then we call that, we change the ending from 8 to ite, because we've, that's just kind of the modification there. The one with more oxygens ends at 8. So like for the standard, so sulfate, nitrate. And these ones you do have to really be familiar with, because to know that nitrate is NO3 minus, that's the only way that you're going to know that nitrite is one less oxygen. So there's some patterns that you kind of have to just become familiar with so that you can work with them. And then when we get to the chlorines, you have a variety of forms. So you've got chlorite and chlorate. Okay, so chlorite has 2 oxygens, chlorate has 3 oxygens, and these all have the same charge, so -1, but lose more oxygens, and you get hypochlorite, so just 1 oxygen, and you add 2, you add a suffix and a prefix, so you get hypo and then chlorite. And then for, let's say you add more oxygen, and so you've got ClO4, then you've got perchlorate, so a prefix and a suffix at the end there. All right, let's say there's a lot of anions that at times end up being acids as well, or they can interact as acids. So we have hydrogens added to them, which makes them acid because acids donate hydrogens or donate protons. So like chloride is the ion, so we change the ending by adding ic acid, so hydrochloric acid, so hydro for the hydrogen, and then the ic acid indicating that it behaves as an acid. So all of the halogens behave that way, so you could have hydrofluoric acid, hydrochloric, bromic. Hopefully you get kind of see the pattern there. Another way it applies, so if we had the chlorite, okay, so chlorite or hypochlorite, in the acid form, it would be hypochlorous acid or chlorous acid. So you change the ite ending with an OUS acid ending, and that gives you a way to decipher what the formula is going to be for that compound. And then if it's an 8, ends in 8, so it becomes ic acid. So chloric acid, perchloric acid. If you think of sulfate, what would sulfate's ending be? So it would be sulfuric acid, because it ends in 8. And so, anyway, I think you hopefully get the idea, or kind of the pattern. And then when we get to molecules, so those were ionic. So we've talked about ionic, we've talked about acids, and now we're looking at molecules, which are named using binary compound naming, so mono, di, tri, tetra, penta, hexa. The less electronegative atom is usually listed first in electronegativity. So knowing kind of the basic pattern of electronegativity on the periodic table, where electronegativity increases as you go to the right and decreases as you go down, allows you to kind of figure out which one goes first. And then you're just going to use different prefixes to indicate the name of the formula. So the only thing that you don't use is mono for the first thing in a compound. So like for carbon dioxide, we would not call it monocarbon dioxide. It's just carbon dioxide. We drop the mono for the first compound. But you can kind of see the basics there. So the prefix ends with an A or an O, and the name of the element begins with a vowel. The 2 successive vowels are often elided into one. So dinitrogen pentoxide. So rather than using pentaoxide, we just call it pentoxide. All right, and then when it comes to organic compounds, there's just kind of basic. So if it's just a compound that's made out of carbons with no background in it, it just goes, just ends in ane, but you use meth, eth, prop, those sort of things. And then you could go deeper into organic chemistry naming because it actually is quite elaborate, but you can go on to take lots of organic chemistry to. All right, so you have alkanes and then meth, eth. And then when you have functional groups, it kind of changes the name of the organic compound. So methanol, ethanol, 1-propanol. Isopropanol would have the oxygen or the OH group in the middle carbon. So it just kind of changes depending on how the compound ends. And we've looked at that in first year chemistry. So